Okay, Unit 4 notes. We're going to talk about circular motion. Uniform circular motion is just the movement of an object with a constant speed around a circle. And the best way to look at that is with vectors. I know this doesn't look like a circle, but basically what you have is if you have an object traveling around a circle in uniform speed, okay, let's say it starts here and ends up here. If I take the actual velocity is always tangent to the circle, the linear velocity, so to speak. So that if the cord were to break, this object would keep traveling horizontally. Well, if I take this vector here, then, which is tangent to the circle, and I place it, next to the other vector here, I'll place them tail to tail here, so that I can find the change in velocity by subtracting them. So I'll place it here. I know it doesn't look quite the same, but if I did this better, you'd be able to see that if I place this here, the change in velocity looks a little short, but you get the idea. The change in velocity is what I get when I subtract these, in which case that would be this vector here, which we know acceleration is equal to the change in velocity over change in time. So if my acceleration vector then is this vector here, so that actual change in velocity, which I didn't draw the greatest, but so what that means is that the acceleration is always pointed towards the center of the circle. I know that's kind of weird, but basically, if you look at your change in velocity, your velocity is always changing in such a way that that change vector is pointed to the center of the circle, which means that we have a centripetal acceleration, which is an acceleration of the object towards the center of a circle. Now, we have a formula for that on the formula sheet. It's v squared over r. And in fact, if I use just simple equations we already know, like distance over time, where the distance would be the circumference of the circle and time would be period, capital T, I could substitute that in for v and simplify to get another equation. And that equation is 4 pi squared r over t squared. And that's on the formula sheet as well. And we can still use Newton's second law with this too. Just keep in mind that the acceleration we're talking about now is the centripetal acceleration, which is towards the center of a circle. Now, let's try an example problem. It says a 13-gram rubber stopper is attached to a 0.93 meter string. The stopper is swung in a horizontal circle, making one revolution. So I'm going to write down the mass. And I'm going to write this as 0.13 kilograms, because we always use kilograms. The radius is 0.93 of this circle, if we're swinging this in a circle. And we know the period as well. It's around in 1.18 seconds. It wants us to find the tension. Now, the force of tension is equal to mass times acceleration. In this case, we have a centripetal acceleration. So the mass is 0.013. The centripetal acceleration, I'm going to use the formula up above, which is right here, 4 pi squared r over t squared. So I'll do this separately. The centripetal acceleration equals 4 pi squared r over t squared. And that's 4 pi squared r is 0.93, and t is 1.18 squared. Whatever I get for this value, I just need to plug in right there, and that will give me the tension force, which ends up being about 0.34. And the units on that are newtons for force, obviously. Okay, the next thing, you've probably heard this word centrifugal force, or centrifugal force. Keep in mind that this force does not exist, okay? So we're going to use centripetal force because the forces that we're talking about when we're traveling in a circle are pointing towards the center. So for us, orbiting around the sun, our acceleration is pointed towards the sun. So we're actually accelerating towards the sun. We keep falling around it because we have some linear speed. But it's not centrifugal force. Centrifugal force means away from, so it means we'd be accelerating away from the object. So why doesn't this force exist? Because we're accelerating towards the center, not away from the center or center fleeing. So this doesn't exist. Now, if you've read those rides at the fair or at amusement parks where you travel around in a circle and you're plastered to one side and it spins, and so you're kind of like stuck against this wall, it feels like there's a force pushing you out away from the center, but keep in mind that's just an illusion of Newton's third law because you're being accelerated towards the center, so forces come in pairs. It almost feels like there's a force that's pushing you outward. It's really just the fact that you want to travel in a linear speed or in a linear direction, but this thing keeps pushing you towards the center. All right, so we can talk about gravity now. Johannes Kepler was an astronomer and mathematician who figured out some laws that are in our curriculum that we're going to talk about First one is the paths of planets are ellipses with the sun at one focus. So we know that we travel around the sun, where the sun is at one focus, and our orbit actually kind of changes from an ellipse to a circle every like 30,000 years or something. And those are called Milankovitch cycles. So we kind of fluctuate between an ellipse and a circle, or we could say the eccentricity of our orbit changes, as you learn about in math class. But nonetheless, he determined that we travel in ellipses, which is a big deal to figure something like that out. But that wasn't it. He also figured out that there's imaginary lines from the sun to the planet that sweep out equal areas and equal time intervals. The best way to look at this is with a picture, like Google Kepler's second law, which I'll do for you. So if you just Google Kepler's second law, look at some of these images, it doesn't matter which one you pick here, but you can see that, here's the months of the years, and it turns out that if we these time intervals are broken down into a month, and each time interval is the same. So here's December to January, January to February, February to March, and so on. He figured out that these areas, that these areas right here are all equal. Okay, and it looks like this area is bigger, but keep in mind it's actually smaller distance from the sun, so it turns out this area is the same as this area. All these areas are the same. That's interesting. I mean, obviously you can deduce from that and from this image that we're actually traveling faster when we're closer to the sun, and we slow down out here. So we kind of slingshot around and slow down, and slingshot around. And what's interesting too is that we're actually closest to the sun in January, and then our summer months we're further away, which is interesting. But we actually get more direct sunlight in the northern hemisphere, and we're going to find out when we study light that the direction at which light hits a surface matters in terms of how much energy is absorbed. So we actually get a lot more energy and more direct sunlight when we're further away, it turns out, and those are our summer months. But Kepler's second law just says that if you have equal time intervals here, which we have in this image, these areas that the planet sweeps out in this ellipse are equal. Kepler's third law then says that, this is a weird one, but the ratio of the period of two objects orbiting another object. So let's just talk about the Earth as object A and Mars as object B. Then the period that it takes the Earth to orbit around the Sun, which is 365 days, and the length of time it takes Mars to orbit around the Sun, which I'm not sure what that is, we can find that in Google really easily, equals, that quantity, that ratio squared equals the ratio of the average orbital distance from the Sun for each, the Earth and Mars, that ratio cubed. So it's a weird mathematical relationship. I don't know how we figured this out, but it's amazing, and we can use it then to find missing information like we can in this problem here. Galileo measured the orbital sizes of Jupiter's moons using the diameter of Jupiter as one unit of measure. He found that Io, the closest moon to Jupiter, had a period of 1.8 days. So we're going to write down this formula right here, which is the period of object A divided by the period of object B squared is equal to the average distance that object A is away from Jupiter in this case, divided by the average distance that object B is cubed. And we're going to use this based on the given information. Now it doesn't matter what units we use as long as we stay consistent, because these are ratios and the units are going to cancel. But Io has a period of 1.8 days, so we're going to use object A. Object A we're going to call Io, and object B we'll call Callisto, two of Jupiter's moons. So the period of Io is 1.8 days. The period of, and it also gives us the average distance, 4.2 units from the center of Jupiter, so that will go over here. And then Callisto had a period of 16.7 days. So we're using days for our period, and we're using just units, which keep in mind 1 unit is the diameter of Jupiter here, but we're using just units for the distance that we are away from Jupiter. So we're solving for Callisto's distance from Jupiter, which is this variable right here. I know this is kind of a weird problem to solve. This is cute. Mathematically, what you guys would do probably is raise both sides to the 1/3, which is actually taking the cube root of both sides. And the easiest way to show you that is now this becomes a 3 in the denominator of that fraction, and this goes away. That's kind of the best quickest algebraic way to do that, and then cross multiply both sides. So then you get the average distance that Callisto is away from Jupiter, r sub b, is equal to 4.2 over this quantity, whatever this number is, which we can find in our calculator pretty easily. So I would enter this into the calculator. If you have trouble with that, we'll work on that in class. That's just a math problem. And you end up getting 18.5 units, or 18.5 times whatever the diameter of Jupiter is. All right.